Hello everyone, my name is Rahim Razaiha. Today we're going to talk about how to use computational fluid dynamics CFD for indoor flow simulation. After this lecture, you will be able to create a simple geometry of a room using ANSYS DesignModeler, do the domain decompositions to prepare it for the grid generation, generate a fully structured grid with local refinements near the regions of interest, and prepare the settings for the simulation using ANSYS Fluent. You will be also able to arrange everything within the ANSYS Workbench. So the outline of the lecture, so we will start with a short introduction to the problem that we're going to simulate, and then we'll go through the details of the geometry creation, the grid generation, and the simulation settings. You can find additional information in the user and theory guides of ANSYS modules, Workbench, DesignModeler, Meshing, and also Fluent. So the introduction to the problem. CFD is a suitable tool for indoor flow simulation. Why is that? CFD can help us design, analyze, and optimize the different heating, ventilation, and air conditioning systems. It can help us assess the indoor air quality and thermal comfort, and also the fire safety and contaminant transport can be analyzed using CFD. So we can do this kind of analysis for indoor environment, for buildings, for cars, for trains, for airplanes, for hospitals like the surgery rooms, for clean rooms in industry, and also for labs with controlled conditions. So it has applications in many different industries. So for example, here we can see the comparison of the CFD results and the experimental data of the temperature inside a cabin of an airplane. So here CFD is used to calculate or to predict the thermal comfort inside the cabin of an airplane. And here you can also see the streamlines coming out of the ventilation or air conditioning ducts of the airplane, which can be used, for example, to optimize the design of the air conditioning or to control or to assess the thermal comfort inside the cabin. So CFD will grant you the possibility to analyze, to design, and also to optimize the indoor condition and different criteria inside the indoor environment in many different industries. So the geometry that we're going to simulate today. So in this tutorial, we'll deal with a very simple geometry. So it's a room, a simple room. The height and width of the room are 3 meters and the length is 9 meters. We have one inlet for the ventilation on one side on the top with a height of 30 centimeter, 0.3 meter, which is going through the full width of the domain. And then there's one outlet for the domain, which is on the opposing wall and on the bottom with the same dimensions. So a very simple geometry. And then the grid that we're going to create for this case is a fully structured grid. And we want to have at least 10 cells along the width of the inlet and also the outlet, 64 cells along the length of the room, and 28 cells along the room width and depth. And then we're going to have stretch cells in a way that we have refined cells near the walls and near the sides of the inlet and outlet of the ventilation system. So we generally refine in the regions where we have higher gradients to increase the accuracy of the simulation. And then we coarsen that towards the region with lower gradients in order to save some computational time. And it means reducing the total number of cells. Now we're going to talk about the details of the creation of the geometry using the ANSYS DesignModeler software. In this tutorial, we're going to demonstrate how to create the geometry and the grid in order to simulate flow inside a room with one inlet and one outlet, what we call indoor flow simulation. As already shown, the room has dimensions of 3 meter height, 3 meter width, and a 9 meter length, and has one inlet on one side of the walls 3 by 3 meter on the top, and on the opposing wall it has an outlet on the bottom. The inlet and outlet has a height of 30 centimeter. We're going to create the geometry and the grid and do the simulation settings using the ANSYS software. The version that I currently have installed is ANSYS 2020 R1 release 1, and I'm going to use the ANSYS Workbench, the main environment, to arrange the connection between the different modules for creating the geometry and the mesh and also the Fluent, the simulation settings. So we're going to do that in different ways. One way, the simpler way, is that we have here as the analysis system fluid flow. We can double click on that, and then we can have one module here which we can use it for creating the geometry. It will automatically be transferred to the mesh generation software and then to the Fluent, and finally for the analysis of the results to the post-processing software. This is one way that is the easier way. We can also easily rename it to indoor flow. The other way that we use the components. So we can add one component here for the geometry, and then one component for the mesh, and also one component for Fluent. Then when we create the geometry, we can easily drag and drop and connect it to this one. So the geometry will be transferred to the mesh, and then the mesh will be transferred to the Fluent for the setup. So this is also the other way. There's no difference between them, but I will prefer this one, which is already prepared for a fluid flow simulation. So I'll select this components and I will delete them. Also this one. Okay, now I have the analysis system. I will just save the file. In one folder, I've selected the name indoor. Okay, and the name and the file is saved. Now, to create the geometry, we have two different softwares inside ANSYS. By the right clicking, you can see that. So we have the space claim geometry and the DesignModeler. You can create the geometry using both of this software, but we will use in this tutorial the DesignModeler geometry. So I will click on this one. So we wait for the module to open. It might take some seconds. But you can see the status here. Start in DesignModeler. Okay, finally we have it. So this is the environment of the DesignModeler. Just one thing that you might notice is that the color of the background that I have here is white, which might be different from the default color that you have. You can easily set it when you come back to the workbench, and then if you go to the tools menu, you have options, and then you have appearance, and then you can select the background color. Okay, we come back to the DesignModeler. So here we see we have different planes: XY plane, ZX plane, and YZ plane. And then here we have the coordinate system. So we're going to create one sketch on the XY plane. So we just click on the XY plane. Then we can see the XY plane. We're going to look normal to the XY plane. In order to set the normal view to the plane, we can easily click on the Z axis here. Then our view will be set normal to the XY plane. Now on this plane, we're going to create one sketch for the room. How to do that? You see, we have the icon here, new sketch. When we have already selected this plane and then clicking on the new sketch, you will see that a new sketch is created just under the XY plane. So we click on the sketch 1, and then we're going to create the sketch. In order to create the sketch, we have to shift from the modeling panel to the sketching panel. So you see we have the sketching panel, we have the modeling panel. So we go to the sketching panel, and we're going to create a rectangle. So I select the rectangle. When I bring the mouse near the origin, you see that a word P is written here, just in the center near the origin. And then that shows that if I now drag the mouse, then the point will be exactly coincided by the origin, or by that point. If I go close to a line, you see that there's a letter C created there. It means that when I drag the mouse and draw a sketch, the starting point will be constrained to that line. So now I'm going to constrain it to the point here. So I drag the mouse, and then I create a rectangle of an arbitrary shape. Okay, now I want to set the dimensions. So from the draw panel, I go to the dimensions panel, and then I have different ways to set the dimensions. So the default is the general, which also gives us the length. So I select it here, and then I can set this line, the length of this line, by 3 meters. And then I select the other line and set the length by 9 meters. Okay, now I need to zoom to fit. So by pressing F7, you can do zoom to fit. You can also do it by clicking on this icon, zoom to fit. Okay, now we can also move this dimension lines by here in the dimensions panel. We have the move. If I select on the move, then I can select this one and bring it a bit closer, and also the other one to make it a bit neater. Then I click zoom to fit, then I can enlarge it a bit. Okay, then I have created my sketch. I come back from the sketching panel to the modeling panel. Now this is only one sketch. Now I'm going to create a surface out of that. In order to do that, I go to the concept menu, and then we have surfaces from sketches. Click on this icon. Now I have to select the base object, which is sketch 1. Okay, confirmed. Remember that we always use the operation add frozen. So change this operation to add frozen. It means that we will create one frozen body. If we use the add material and we create several geometries, they will be combined with each other. But here we need separate modules. That's why we use the add frozen. Okay, then also one thing to remember, always to confirm the action, you need to press the generate button unless the action is not completed. Okay, by doing that, now we see that we have a surface created. The color shows gray. Okay, now I rotate it a bit with the middle bottom of the mouse, zoom out a bit with the roller. Okay, we see the plane. Now we're going to extrude it to create the volume. How to do that? We have the extrude tool here. So we click on the extrude, and for the geometry we select this face. Here we're going to extrude this face. Again, we change the add operation to add frozen, and now we have to select the direction vector. So we're going to extrude it in the Z direction. So you can select the XY plane, then it will be normal to the XY plane. So by confirming the action, so you can also change the direction of the extrusion to -Z or +Z. Now we stay with the +Z. And then we have to set the depth of the extrusion. We set it by 3 meters. And again, we have to press the generate. Okay, now we have our volume. We can rotate it a bit. Okay, now we have our volume. So you can see that now we have 2 parts. This is 2 parts, and then we have also 2 bodies. So in this tutorial, we're not going to go through the difference between the parts and the bodies, but in other tutorials, we will also describe them. So now we no longer need the surface. So I just suppress the surface. Now I only have one volume. So we can also set the volume as fluid, because we're going to create the fluid. Now we're going to simulate the fluid inside this room. Okay, now so that the color or the transparency changed a bit after we selected that to as fluid. Okay, now we have the volume. Now we're going to create the inlet and the outlet for the room. How to do that? There are also different ways, but the easiest way is that we select this face, that the inlet will be on top of that, and then we try to create a new plane based on that. So you see that we have icon new plane, and then if we select it, then we have a plane 4 created here, which you can also see it here. So we click on generate. Now I turn the view normal to this plane. Rotate the geometry a bit. I need to put something a bit hard under my hand. Here. Okay, not this view, yes. Okay, maybe it's easier with this icon. Okay, so this is the new plane that I created. Just for checking, we come back to the original plane, just the XY plane. So you see that now we are a bit rotated. I have to come back to the original position so that we know the top and the bottom. Okay, so this is the original position. Now I select the plane 4 again. Now we're going to create the new sketch for the inlet on top of that. Okay, so here again we have selected the plane 4, and then I select the new sketch. The new sketch is formed under the plane 4. I click on that, and then I switch from the modeling panel to the sketching panel. And then I create a rectangle. Again, you see I go to the point and I see the P. I know that it's constrained to that location, and then I continue with drag until I see the letter C, which means that the end will be constrained to the line, and then I release the mouse. Okay, now I have the inlet with an arbitrary dimension. Of course, the depth is the depth of the room because of the constraints, but the height I'm going to set it using the dimensions. So I switch to the dimensions panel, and then I select the general. I select this dimension, and I set it at 0.3 meter. But going back to the modeling panel, we see that we have created this sketch. Now we're going to create a surface out of that. So we go to the surface from sketches. We confirm the sketch, just sketch 2, and then I change it again to add frozen, and then I click generate. Okay, now I have the second surface body, which is the inlet. But I don't need a separate surface for the inlet. I just need to project it to the wall of the room. So how I do that? Also, there are different ways to do that. I can project the whole face, but I can also project only one line, and then I will have what I want. So I select the line on the bottom of the inlet, and then I go to the menu tools and then projection. The line is selected as the edge. I confirm it, and the target will be this face, and then I click generate. This face, I don't need it anymore, so I just suppress it, and then by clicking on the face of this wall, I will see that, okay, so now I have two different walls. One is the bottom, and then one is the inlet on the top. So this is what I wanted. Now we also have generated our inlet. Now we have to generate the outlet exactly on the opposite wall, but on the bottom. So I rotate it. We do it exactly the same way that we did for the inlet. So I select this face as a base, and then I go and create a new plane on top of that. So you see the new plane will be here. I confirm the new plane, click on the new plane, I click on the new sketch, and then I will have a sketch 3 based on that plane. I switch from the modeling panel to the sketching panel. I select the rectangle. I'll go to where I see the letter P. It's a bit maybe difficult. I have to zoom a bit. So I click again. Yes. I have the letter P, and then I continue until I have the letter C, which means that the constraints are correctly set. And then I set the dimension for the outlet also at 0.3 meter. Okay, now the outlet is also created. Note that it could be a bit difficult when you want to drag and drop to go for the these constraints, automatic constraints, but you can also do it in other ways. You can create it without the constraints, but later set the dimensions. For example, set the dimension of this wall to this axis at 3 meter. Then you're sure that the distance from here to there is equal to the size of the building wall or the room wall, and then you can also set the length of the line as 3 meter. Then you're sure that this constraint is satisfied. On the other hand, you can also set this dimension as 0.3 meter, and then finally the distance from this line to the top at 3 meter. Then you're also sure that this is positioned correctly. But this, using an automatic constraint, makes it a bit easier. So I have created the sketch for the outlet. I go back to the modeling panel. Similarly as the inlet, I'm going to create a sketch, a surface from the sketch. So I click surface from the sketch. I select the base as the sketch 3 already selected, and then I change it to add frozen and then generate. So now I also have this outlet geometry here. You can see that. Now again I need to impose the line, project the line on this face. Okay, same way as before. So we projected this line on this face. Now if I suppress the outlet, then you will see that this wall is also decomposed into 2 parts, the outlet and the rest. So now if I select on the original XY plane, zoom out a bit and rotate the geometry, then we can see a bit better. Yeah, we have the room, we have the inlet and the outlet. I hide the sketch 1. Okay, now we only see the room. Okay, it's easier then. So now we have what we want. Now we have to make some extra changes in the geometry, but the purpose of that is to help later on with the grid generation. Because we're going to create a fully structured grid for this geometries, for this simple geometry, we need to make some divisions in the lines so that we can later use them to set the sizing in the grid generation. To be more specific, near the inlet and near the outlet of the room, we want the grid to be finer. So we have to have some control over the grid in these regions. So this is the inlet of the room, and on the opposing wall, this is the outlet of the room. So we're going to have some control over the grid in these regions. Because later on we will be using the edge sizing for this edges. Here it will be no problem because we have one separate edge that we can set the sizing, and we have separate edge here. But on the opposing wall here, we need to also have some face similar to the inlet, the same dimensions, so that we can set the sizing exactly in a structured way. Also the same holds for the outlet. So what I mean is that I need to project this line on the opposing face here. Now, if we come back to the isometric view, we will see that we have the inlet, and then it is projected on the other face. Now we have the outlet. We're going to also project it on the opposing face. So I select the edge of the outlet. I select the projection. Now I confirm the edge. I rotate the domain, the geometry, and then as the target I need to select this face, and then I click generate, and then we have the projection of the outlet and the inlet. So now the geometry and the decomposition of the domain for the grid generation is complete. Now what we're going to do later on is setting the boundary conditions. So as we discussed, here we have the inlet. So we select this face, and then we right click, we have the name selections. For the name selections, we set the name as inlet. This will make sure that in the simulation software Fluent, it will automatically be recognized as the inlet. And then we click generate. Don't forget to click the generate button always. So now we check it. Inlet is set here. Now we're going to also set the outlet. Select the face of the outlet, same way, name selection and outlet, and then generate. Okay, now the outlet is also set. The rest of the faces are the walls. So we select all the remaining faces here, 1, 2, 3, 4. I rotate it. 5, 6, 7. And then we have 8. And then we rotate it to check. So here we have the inlet not selected. So on the sides we have it. On this side we also have all the walls selected except the outlet. Now I right click, name selection, and I put the name as walls. I click generate. So this will also make sure that these faces will be recognized as walls inside the Fluent software. So now we are done with the geometry creation. And the geometry is ready for the grid generation. So we have one volume. We select the volume, and then we set it also as a name selection as fluid. So we have set also the boundary conditions. We have inlet, we have the walls, we have the outlet on the other side here, and then we have the fluid, which is the volume, the whole volume. And then here when we look, we have three surface bodies, which we use them, and then we don't need them anymore, so we have suppressed them, and then we only have one volume, which is set as the fluid. Okay, the geometry is ready, so now we save the project. Geometry is saved. Now we can close the ANSYS DesignModeler. And now you see that the geometry by the DesignModeler, by the DM, is finalized. So we have the tick here, geometry is created, and then we can double click on the mesh or go to the next step. So we wait a bit also for this software to open. So see starting meshing. Okay. After the ANSYS Meshing software is opened, then we can see the geometry that we created. So I select the global coordinate system so we can see it here, and then I try to rotate the geometry so that we have the inlet here. Now we have the name selections, and then we can see the boundary conditions. So we have the inlet, we have the walls, we have the outlet, and on the other side here, and then we have the fluid volume. So we have set the geometry, and now it is time to set the sizings for the grid, for the computational grid. For this geometry, we're going to have 10 cells along the width of the inlet and outlet, and then we're going to have 28 cells in the small dimension of the room and 64 cells along the large dimension of the room. So we're going to start. So we select the wall, we select the edges around the around the room, the 9-meter long edges, and then so we have 4 of them. We have selected them, and then we go on top of one of them, we right click, we have insert, and we have sizing. So now you see that the cells are located here. Now we need to also set some growth ratio. The default setting is the uniform distribution, but we're going to set some growth ratio so that the cells become finer, close to the inlet and outlet, and then become a bit coarser or larger near the middle of the room. This is because we assume that, or we expect that near the inlet and outlet of the room we will have higher gradients, so we need to have a smaller or finer grid to be able to have more accurate solution. And then in the middle of the room we have less gradient, so we can have larger cells. Okay, so as we discussed, we're going to have 64 cells. So there are 2 ways to set the sizing for edges. We can set element size, and then we can set number of divisions. So here we're going to set number of divisions. We set it as 64, as we mentioned. Now we're going to set the growth ratio. So we need to set a bias. So the bias type. Now you see that we have no bias. It means uniform distribution. Now we're going to set the sizing in a way that it is coarser in the middle and finer on the sides. I try to enlarge this details of the sizing a bit, and then so we have also two ways to set the bias. We have a bias factor, but we're going to use a smooth transition. So now you already can see that this is reverse of what we want. So now we have the sizing finer in the middle, but this is not what we want, so we change it to the opposite. So now we have the coarser in the middle and finer on the sides, and then the growth ratio we will use 1.13. So note that this is based on the previous experience on this geometry to generate a smooth grid. But for any new geometry, you have to find a growth ratio that can give you a smooth grid. And then how do you do that? You have to start with one value, check the grid when you generated that, and then optimize the value by try and error. So this value has been tested to give a smooth grid for this geometry. So now I set the value for this long grid. You can also rename it here so that you can remember. For example, you can set edge 9 meter, or you can leave it as the default. So I just rename it just to see also this functionality. Okay, and then we go to set the sizing for the other edges. So let's select the other edges that we're going to set the sizing for. Okay, now I selected 4 edges on this wall, and 4 edges on the opposing wall, 4 edges on this wall, and 4 edges on the opposing wall to set the sizing. So in total 8 edges. I right click on that, also the same way insert sizing, and here now we're going to use, as we discussed before, 28 cells. So we put 28 cells. Again, the default distribution is uniform, but because we have walls on the side, we're going to have finer cells near the walls, because again we expect to have some gradients there because of the presence of the wall and the no slip condition on the wall, which will lead to creation of a velocity profile. So we have to create a type of bias. So I changed the bias from no bias to a type of now into this distribution, but now again we see that we have the cells finer in the middle. I changed the distribution to the reverse. Now we see that it's correct. So we have coarser cells in the middle and finer closer to the walls. So this is what we wanted. And then I set the transition ratio to 1.3. Again, I repeat that this value is based on the test to give a reasonable or smooth grid sizing distribution for this geometry. But for any new geometry, you have to find this value, like the optimal value for this sizing, so that you can ensure that you don't have any jump in cell size in your grid. Okay, now we also set this sizing. Now we can go to set the sizing for the edges of the inlet and outlet, for the small edges of the inlet and outlet. Okay, so now this is the second sizing. Now we go to select the other walls, to other edges. So we have one. I have to rotate it a bit. Okay, so let me rotate the geometry a bit. You can also change it to change the view to a wireframe. Yeah, this one. This view can help me to see the edges a bit easier. So I select the edges. We have okay, now we could select it, one edge here, one edge here. Then we also have one edge here and so one here. So 4 already selected. So 5, 6, 7, and finally 8. So we could select all of them, and then we give a sizing to them. So as we discussed, we will give 10 cells here. So we have 10 cells. Again, the distribution here is uniform, but we're going to also give a bias here for the same reasons. So then on the sides of the inlet and outlet, we expect to have more gradients. So we're going to refine the cells near the sides. So I will give a bias here. We have to check, yes, this is towards the side. I will set the smooth transition ratio as 1.3. So now we're going to check all of them. So if I zoom in, you will see that it's finer on the sides, coarser in the middle. And then we can check that for all of them. So here is also the same. The same holds here. Also the same here and here. So the sizing for these edges are also set correctly. So now there's only one edge or one set of edge remaining, and that's the edges in between the inlet and the opposing walls and also the outlet. So what I mean is this edge. So the inlet between the edges between the inlet and the projection of the outlet, and the same between the outlet and the projection of the inlet. So 4 edges in total. So now we also have selected them. Then we put the sizing. Also here we're going to set 28 cells. So we'll have 28 cells. And then here we also set the distribution, the bias, to have finer cells near the inlet and outlet. And then I will use a smooth transition ratio of 1.2. And then we can already see that the distribution is also correct. It gives us finer cells near the inlet and outlet. So you can see that here. It's also correct for all the edges. Okay, so now we set the sizing for these edges, okay, and then we set the sizing for the inlet and outlet, correct, and then we set the sizing for the rest of the 3-meter length edges, and also finally for the long edges. So I think we selected the edges for the sizing for all the edges. Now it's time to right click and click and generate mesh. Okay, now the mesh is generated. Maybe in wireframe we cannot see it well, but this is better shown in this view. So now let's see. Okay, so now let's look normal to that. Now let's look normal to that. So we see that we have larger cells in the middle and finer cells on the side of the wall. If we look on the side, we can see that, so these are the inlet and outlet. So near them, we also have a distribution that we want, finer towards the sides and coarser in the middle. So also here. And then finally, the top view also shows us, so this is the inlet and the outlet. And then we have also the refinements that we want. So the grid is ready. Now we can check a bit the statistics for the grid to see how many cells we have. So here in the statistics panel, we can see that we have about 100,000 nodes and elements. So this was about the generation of the grid for this geometry. Now, one thing that we should still note is the general settings of the grid generation software. Because in the Workbench, we use the analysis system Fluid Flow. Here in the general settings of the grid, everything was already prepared for us. So the physics preference was CFD, the solver preference was Fluent. But if we use the general component that we at the beginning talked about, that this is the other way, and then we just drag and drop the geometry inside that, and then we start to open the module ANSYS Mesher. Just wait for that. Then we will see that these general settings are not already defined there, because this general module mesh works both for CFD, like fluid simulations, and also for mechanical simulations. That's why then you need to set your preference, and then this affects your grid generation and grid settings. So that's why you have to note that. So now let's take a look at that. So this is the mesh, and this is the general settings. Now you see that the default of ANSYS Meshing software is mechanical for the physics preference. Now if you use this module, you have to remember to change this to CFD and make sure that the solver preference is Fluent, because there are also other software options here like CFX or Polyflow. So it should be Fluent. So this is also something else that you should note. So I close this one and try to, select it and try to delete this module. Now coming back to the grid, then we see that we did all the settings. The grid is ready. So this grid is fully structured. So the orthogonal quality should be 1, but we can always check the grid quality also here. And then you can use different metrics. For example, mesh metrics. You can use the skewness that here, because it's fully structured grid, and then the skewness is 0 because everything, the grid is orthogonal, quad cells. But we can check, for example, the aspect ratio. We have a minimum of 1 aspect ratio of the cells and maximum of 4 to 5. The average is about 8. And then here you can also see the mesh matrix. And then you can select these cells to see this column to see which cells have this aspect ratio. And then also you can select here. So these cells have higher aspect ratio, and these cells have higher aspect ratio, and finally here, which is the cells here. So also about the other metrics. So if you do, for example, unstructured grid is very good if you check the skewness, because if you have highly skewed cells, then your simulation might diverge. So it's better to check the skewness level here, and then if you have high skewness, based on this matrix, you can find which cells are the highly skewed cells, and then modify in that region. So now I finished the ANSYS Meshing module and save the project. Now everything is ready to set up the simulation settings in Fluent. Okay, now we are ready to go to the last step, which is doing the simulation settings in ANSYS Fluent. Remember that in this tutorial, we assume that you are already familiar with ANSYS Fluent environment, and you know how to set the models, the discretization order, etc. So we're not going to explain that. So we're just going to do the settings for this specific simulation. Now we're going to do the last step, which is preparing the setup in ANSYS Fluent. So we have the geometry and the grid ready. Now we're going to open ANSYS Fluent. So we double click on the setup and it will start ANSYS Fluent. So we're going to go for double precision to increase the accuracy, and also we're going to display the grid after opening the case. So we will have, now we're going to open Fluent in using one processor, but to increase the calculation speed when you're going to do the simulations, you can go for the maximum number of cores that you have on your computer. So let's start. Okay, the Fluent is coming. Yes, here we have the Fluent environment. Here we have the GUI, the graphical interface, and here we have the TUI, the text user interface, that we can also do the settings using text commands or using the graphical interface. So in this tutorial, we will work with the graphical user interface. Okay, so the grid is still loading, so it might take some seconds. Okay, it's ready. Now we can see the grid that we created. Now let's do the settings for the simulation. Okay, so the first thing, so now we check the grid to see if everything is okay with the grid. So here we can change the size of this panel. So what we check always is the minimum volume. We should never have a negative minimum volume. That might lead to a divergence. And then the rest, if there's any error, it will be shown when you check the grid. You can also set the scale. So we have a room from 0, 0, 0, and also the maximum values of x, y, and z are 9, 3, and 3. So these are the values that we set, and the unit is meter. So everything looks to be okay. Here you can also check the quality, so here is a fully structured grid, so the minimum orthogonal quality is 1, which means that all the cells are quad cells, and the aspect ratio, the maximum aspect ratio is 48. So let's do the settings. So we're going to go for pressure-based solver because we're going to simulate incompressible flow here, and then the simulation is steady, so we don't have variations in time. Okay, now we're going to set the models. So for the turbulence model, in the newer version of ANSYS Fluent, default is the SSD K omega model, but for the indoor flow simulation, we usually use the K epsilon RNG turbulence model. Here we're going to use the standard wall function, but for indoor flow simulation, we usually use the enhanced wall treatment. So this option, and then so we also use the okay, so we typically use the enhanced wall treatment for low Reynolds number modeling, but because this grid that we created is not the perfect grid in terms of the low Reynolds modeling simulation, and the Y star value on the walls is a bit high, so we're not going for that approach. So here we will only use the standard wall function. So I click OK, so K epsilon RNG with the standard wall function. So the model is set. Now we're going to set the boundary conditions. So here we have the boundary conditions for the inlet. Now we're going to set the inlet value, so the velocity magnitude. We have 0.455, and for the turbulence specification, we're going to use K and epsilon, and the values of K and epsilon. So we have the velocity U, the velocity magnitude, and then based on a turbulence intensity of 4%, we can calculate the value of K. So the value of K can be calculated using the equation K equals 1.5 times parentheses the turbulence intensity times the velocity magnitude, close the parentheses to the power of 2, and then this will lead to a value of K, which is 0.000496686. And then the value of epsilon can also be calculated using the value of K and also using the turbulence length scale. So the turbulence length scale here can also be considered as a tenth of the height of the inlet or outlet channels. So here is the inlet. So it's a 0.3 meter. So the length scale, the turbulence length scale will be 0.03 meters, so 3 centimeter, and then epsilon is equals K to the power 1.5, and then divided by the turbulence length scale. The value will be 0.000369. So we confirm the settings for the turbulence for the inlet, and then we check the outlet. For the outlet, we have pressure outlet, so it's the zero static gauge pressure, and then we set the same values for K and epsilon. For K 0.0000049,686. And then the epsilon is 0.000369. Okay, and then we also confirm this. Okay, now we also set the outlet condition. Now we can go to the solution methods. So here, so we open this panel, we increase the discretization order to second order for K and epsilon. Okay, and then we go to the controls. We increase the limit for the maximum turbulent viscosity ratio to 1E20. And then we go to the residuals. And then we change the, and here in the residual monitors, we change the convergence criteria to none. So based on this convergence criteria, the simulation will stop when the scaled residuals drop to 1E-3 for each equation, for all the equations. But now we change it to none. It means that the simulation will not stop based on the criterion, but based on the number of iterations that we put in. And then to speed up the calculation, we're not going. And then to increase the calculation speed, I turn off the print to console so that we don't see the residuals being printed here. We only see a plot here. And then the values to plot, you can keep it as 1000 or you can increase it to 5000. And then the values to store, we can, for example, increase it to 10,000. And then I click OK. So the monitors are also set. So now we have to initialize the simulation. So here we initialize it by the inlet. I press initialize. So the solution is initialized. Now the only thing that we still need to do is to set the number of iterations. For example, you can set it at 5000. And now everything is ready. And then by pressing the calculate button, the iterations will start. So now here we're not going to do the iterations. So I just save the project here. Okay, the project is saved. Here we also have the option to export the case and data file for Fluent. So the difference is that the case, it contains all the settings that we did, but actually no data, no solution. But the data is the solution. For example, now we have initialized the simulation. So with the inlet value, so throughout all the cells in the domain, we have the inlet value. So this is now the solution. But after doing the iterations, we will have the converged solution, and that will be stored in data file. So the settings is the case file, data file is the solution. So we can save the case, export the case and data file to any location that you want. There, you can open the case and data file as a separate module, as a separate Fluent module, and you don't need to do it within the ANSYS Workbench. You can open the Fluent and open the case and data file. For the final calculations, I recommend you doing the calculations outside the Workbench environment, and the experience has shown that the Fluent goes faster when you open it as a separate module and not inside the ANSYS Workbench. So that was the end of the settings for the Fluent. So now we can close the ANSYS Fluent. And then you see that we also have now the tick for the setup. It means that the simulation is ready, but we still have no solution. So we need to iterate. Okay, as a summary, we illustrated how to do all the steps for an indoor flow simulation. So we went through creation of a simple geometry of a room with an inlet and outlet using ANSYS DesignModeler. We decomposed the domain to facilitate the grid generation. We generated a fully structured grid with local refinements in regions of interest, and we prepared the setup in ANSYS Fluent for the simulation. And everything was ironed within the ANSYS Workbench. So now you are ready to do your own simulation for an indoor flow.